The board that left no trace. In a Chinese tomb of the Western Han Dynasty, sealed around 2,000 years ago and opened in the early 1970s, the excavators found a small silk pouch. Inside it were rods cut from bone, each about as long as a pencil and no thicker than a matchstick. These are counting rods. For something like 2,000 years, rods like these were how arithmetic was done in China, laid out in patterns on a flat surface and shifted about by hand. Similar bundles, in bamboo, in bone, in ivory, have come out of graves in 4 provinces. At one tomb, a set of rods turned up in a lacquer box alongside a gaming board and a handful of gaming pieces, which are very easily mistaken for counting rods. These are the physical remains of a computational practice. They are also, very nearly, all that is left of it. Rods survive because bone and ivory and lacquered bamboo survive. The surface they were laid on, which is where the thinking happened, does not survive. Nobody knows what that surface was. Historians have proposed a tabletop, a wooden board with a ruled grid, a board without a grid, a cloth, a mat, sand, or simply the floor. Any of these would work. None would survive except by accident, and a surviving one would be very hard to recognize. So the apparatus at the center of 2,000 years of Chinese mathematics is known entirely from instructions for moving things around on it. The ancient texts say to place a number here, to move a column there, to multiply throughout and then subtract directly. They assume you are standing in front of the thing they never name. That is the odd situation the book called The 9 Chapters on the Mathematical Art comes down to us from, and the book keeps landing back in it, over and over, across the next 2,000 years. 4 of its 9 chapters survive only because an 18th century scholar dug them out of a 15th century encyclopedia that had cut the book apart and refiled the pieces under subject headings, and because he then repaired what he found. Anything quoted from those chapters reaches us only through his reconstruction. Its author is unknown. It has 9 chapters and 246 problems. It reached something like its present form in the 1st century of the Common Era, though it contains older material and the oldest layers may go back several centuries further. Each chapter is named for the kind of work it does. Rectangular fields is arithmetic with fractions, dressed as land measurement. Millet and rice is proportion, dressed as grain exchange. The other 7 are named the same way, after the administrative task that gives the mathematics its clothes. Every problem is a small scene. A field of such and such dimensions. A shipment of grain to be split among counties at different distances from the capital. 5 families sharing a well. A magistrate and his clerks working out how many chickens they can afford. Nothing is stated abstractly, and there is no theorem anywhere in the text, because the text is built out of procedures rather than propositions. Chapter 8 is called Fangcheng. The first character, Fang, is unambiguous. It means square or rectangle. Argument over the second, Cheng, goes back at least to the 3rd century. Liu Hui, the earliest commentator whose work survives, glossed it with a term borrowed from tax administration, a word for assessing quantities against fixed rates, then defined the compound as a rectangle of measures. A 13th century mathematician, Yang Hui, put it more simply. What is called rectangular, he said, is the shape of the numbers. Not a relation between quantities, then, and nothing that a modern reader would recognize as an equation, but a physical arrangement on a board. Chapter 8 poses 18 problems of one kind. Several quantities are unknown. Several facts are given that relate them to each other. Find each quantity. A modern mathematician would call this a system of simultaneous linear equations. Chapter 8 gives one general procedure meant to solve them all, and that procedure is entirely a description of where to put rods and how to move them. Since the end of the 19th century, Fangcheng in Chinese has simply meant equation. The modern sense was read backwards onto the old word, which invites everyone who opens the chapter to see modern algebra sitting there in disguise. There is no symbolic algebra in Chapter 8, no letters standing for the unknown quantities, no equal sign, no expression being transformed, nothing at all that could be written on a line. Problem 1 sets the pattern. 3 bundles of superior grain, 2 bundles of medium, 1 bundle of inferior, yielding 39 measures of grain between them. Then 2 more conditions like it, with the proportions shuffled and the yields different. How much does a single bundle of each grade yield? The instructions begin by telling you to place the first set of quantities in the right-hand position, and the other 2 beside it. Each condition becomes a vertical column. Columns run right to left in the order the problem gives them, because that is the direction Chinese script runs. Within a column, the quantities sit top to bottom in fixed order, with the total at the bottom. What appears on the board is a grid, 1 column for each condition, with a row for each kind of grain and a last row for the totals. Once the array is laid out, 2 operations do all the work. One is Fangcheng, which means multiply throughout. You take a single entry from one column and multiply an entire other column by it, term by term. Its partner is Zhai Chu, direct subtraction, meaning that one column is subtracted from another repeatedly until the top entry of the target column vanishes. Liu Hui glosses it. Let the column with less subtract from the column with more back and forth repeatedly, and then the head position must be exhausted first. Work right to left, top to bottom, and the array collapses into a triangle with one column reduced to a single quantity. That gives you one of the answers. Knowing it, you can climb back up the columns and read off the others in turn, which is the step now called back substitution. The procedure never divides during the elimination. Nothing in it produces a fraction in the middle of the calculation. Every entry on the board stays a whole number from the first move to the last, with every division held back until the very end, when the answers are read off. In Problem 1, the procedure arrives at the numbers 333, 153, and 99, all of them weighting over a common divisor of 36. Only then does anyone divide, giving 9 1/4 measures for the superior grade, 4 1/4 for the medium, 2 3/4 for the inferior. Deferring division that way is a deliberate discipline, and its reason is physical. A fraction on a counting board is expensive. It has to be held as a pair of numbers occupying space, tracked through every subsequent operation, and reduced by hand. An algorithm that generates fractions in the middle of a 5-column elimination generates dozens of them, until the board fills with bookkeeping. An algorithm that defers every division until the end runs on whole numbers throughout, and finishes with 1 division per unknown quantity. Everything about it is shaped by the medium it runs on. 17 of Chapter 8's 18 problems range from 2 unknown quantities up to 5. Problem 13 is the odd one. It has 6 unknown quantities and only 5 facts relating them. Problem 13 is about a well. 5 families share it, and each family has a rope, and none of the ropes is long enough on its own. 2 of the first family's ropes fall short by exactly the length of the second family's rope. 3 of the second family's ropes fall short by the length of the third family's, and so on down the line, 4 and 5 and 6, each family's shortfall made up by the next family's rope. The 5th condition closes the circle. 6 of the 5th family's ropes fall short by exactly the length of the first family's rope. Given all that, how deep is the well and how long is each rope? Anyone with modern training sees immediately that the question has no single answer. 5 facts cannot pin down 6 quantities, so infinitely many sets of ropes fit, every one of them a scaled copy of every other. Chapter 8 does not hesitate. It gives a well depth of 721, with rope lengths of 265, 191, 148, 129, and 76, then moves on to problem 14. 721 is 2 times 3 times 4 times 5 times 6, plus 1. That combination of the numbers is what modern algebra calls a determinant, a single value squeezed out of a square block of them and used to solve the system they came from. It is the determinant of the numbers the 5 conditions supply. Liu Hui's commentary makes clear that 721 arrives first, before anything has been decided about the depth of the well. Answers, he says, are stated as Liu as ratios. He is telling his reader that these numbers are a set of proportions, so that any scaling of them will do. Generalize the well to any number of families, and the longest rope in each case turns out to be a derangement number. Imagine a party where everyone leaves a hat at the door and every guest goes home in somebody else's. The number of ways that can happen is a derangement number, and for 6 guests, it is 265, the exact length of the longest rope in the 9 chapters. That result dates from 2018. Early in Chapter 8, in the course of solving Problem 3, the procedure generates a negative number, and the text stops to deal with it. Chapter 8 calls the passage the Zhengfu Shu, the procedure for positive and negative. It runs to 8 terse clauses, 4 for subtraction and 4 for addition. Like signs subtract. Opposite signs add. A positive taken from nothing becomes negative, and the other 5 clauses follow the same shape. Liu Hui explains the odd phrase about nothing. It means, he says, that there is no counterpart. There is nothing in the corresponding position of the other column, so the operation is with 0. That is the first appearance anywhere in the human record of rules for adding and subtracting negative quantities. The Indian mathematician Brahmagupta writes his rules for negatives, framed as debts and fortunes, in 628. Even on the most conservative dating of the Chinese text, the one that credits nothing earlier than Liu Hui's commentary in 263, the 9 chapters is ahead by 3.5 centuries, and on the standard dating it is ahead by 600 years. Al-Khwarizmi, the 9th century Baghdad scholar whose name gives us the word algorithm, uses no negative quantities at all. In Europe, the first satisfactory treatment is by the Italian physician Girolamo Cardano in 1545, and even Cardano splits one kind of problem into 13 separate cases so as to keep every quantity in it positive. Hand practice made the distinction chromatic. Liu Hui states it plainly. Positive rods are red, negative rods are black, the reverse of the accounting convention that later took hold in Europe, where being in the red is the bad direction. There is a fallback for anyone working with only one color of rod. Lay the negative ones slanting across the position instead of upright, and the distinction is preserved in geometry rather than pigment. By the 6th century, rods were being made with triangular cross-sections for positives and rectangular ones for negatives, so that the sign could be felt as well as seen. Printed texts, later still, marked a negative with a diagonal stroke through the last digit. To call something negative, Liu Hui writes, is not necessarily to say it is deficient, and to call something positive is not necessarily to say it is abundant. He has understood that the sign is a formal marker attached to a position in a calculation, and that its meaning is exhausted by the rules governing how it combines. Almost nothing is known about Liu Hui. There is a date, 263, given in a source written 4 centuries after the fact, which historians take to be copied from a lost preface or colophon. Scholarly guesses at his birth and death years are spread across a 75-year window, and they remain guesses. He wrote a commentary on the 9 chapters, a short surveying manual, and nothing else that anyone recorded. The commentary is a work of textual archaeology, as Liu Hui says himself in his preface. In the past, he writes, the tyrant Qin burnt the written documents, and canonical learning was scattered and ruined. He means the first emperor of the Qin dynasty, who unified China in the 3rd century before the Common Era, and who is remembered, rightly or not, for ordering the burning of the classics. Afterwards, 2 Han officials, Zhang Kang and Zheng Shaocheng, both renowned for skill in calculation, took the surviving remnants of the old text and each in turn cut away and supplemented what they found. That is Liu Hui's account of how the book in front of him came to exist. It is not independent evidence of anything, since he is reconstructing a history he did not witness from a text he inherited, but it tells you what he thought he was doing, which was commenting on a salvage job. His preface also contains a sentence about method. Things of the same kind, he says, are inferred from one another, each returning to where it belongs, so that although the branches divide, they share a single trunk, and one need only set out from a single starting point. Liu Hui's ambition throughout is to show that the procedures of the 9 chapters are not a heap of separate tricks. Adding fractions and solving a 5-column linear system, he demonstrates, are the same operation. Both consist of making things homogeneous and making them equal, of scaling quantities so that they can be compared and then combining them. He gives the operation a name, Kai Tong, then uses it to tie the book together. His most famous demonstration cuts a circle. He inscribes a regular hexagon in a circle, then doubles it to 12 sides, then 24, 48, 96, 192, computing the area at each stage. From the 96-sided and the 192-sided figures, he brackets the circle's area between 2 values, and states his result as a pair of ratios. Circumference ratio 157, diameter ratio 50. That is 3.14, the number now called pi, and he notes carefully that his value is slightly less than the truth. The received commentary contains a further and better value, 3.1416, arrived at by an acceleration that avoids 4 more square root extractions. Whether that passage is Liu Hui's own or a later Han's has been argued over since the early 20th century, and is not settled. He explained why the method works. Cut it finer and finer, and the loss grows smaller and smaller. Cut it and cut it again, until it cannot be cut any further, and then it coincides in body with the circumference of the circle, and nothing is lost. That is a limit argument, stated in the 3rd century. He needed it for more than circles. Chapter 5 of the 9 chapters asserts, without justification, that a certain wedge splits into a pyramid and a smaller solid in the ratio of 2 to 1. Liu Hui set out to prove it. He cut both solids through the midpoints of their edges and found that each fell apart into blocks that are immediately in the right ratio, plus a leftover that is a smaller copy of the original problem. Every round of cutting removes 3/4 of the remaining volume and leaves a quarter behind. Liu Hui saw exactly what this meant and wrote it down. Have them smaller, and the remaining dimensions grow finer. The extreme of fineness is called the subtle. That which is subtle is without form. When it is explained this way, why concern oneself with the remainder? In 1844, Gauss observed that the volume of a pyramid seemed to require a limiting argument. Hilbert put the question on the famous list of 23 unsolved problems he set before mathematics in 1900, where it is the 3rd, and Max Dehn answered it within 2 years. A regular tetrahedron, the solid with 4 identical triangular faces, cannot be cut into finitely many pieces and reassembled into a cube of the same volume. For pyramids in general, no finite dissection will do, which is why Liu Hui could not close his argument by cutting alone. 16 centuries before anyone could state that theorem, he had identified the remainder as something to be argued away rather than removed, then argued it away. Spheres defeated him. The formula the 9 chapters gave for the volume of a sphere was wrong. Liu Hui showed that it was wrong, then constructed the solid, which he called the box lid, formed by intersecting two cylinders at right angles inside a cube, and argued that the sphere fills the same fraction of it that a circle fills of the square drawn around it. On a comparison of cross-sections, he could not yet justify. That reduces the problem to finding the volume of the box lid. He wrote his surrender as verse. He wished to offer his humble reflections, but feared he would miss the correct principle. He dared to let the doubtful points stand, waiting for one who could expound them. It took about 250 years. Zhu Changzhai, in the 5th century, pushed Liu Hui's polygon method far enough to fix pi to 7 decimal places, a record that stood for something like 1,000 years, and gave the rational approximation 355/113. His son Zhu Zhengjai solved the box lid, using a principle recorded in 9 Chinese characters that translate to roughly this. Since the cross-sectional areas at corresponding heights are the same, the volumes cannot differ. 1,100 years later, with no known line of transmission between them, Bonaventura Cavalieri arrived at the same principle in Italy, and in Europe it carries his name. Father and son wrote their results in a book called the Zhui Shu, The Art of Mending. It was lost around the 10th century. Zhu Zhengjai's principle survives because a 7th century editor copied it into a commentary on the 9 chapters. The editor was Lai Chunfeng, an astronomer and court official. In 656, he and 2 colleagues presented to the throne an annotated edition of 10 mathematical books, which became known as the 10 computational canons and served as the official curriculum of the Tang State School of Mathematics. He also wrote the treatises on astronomy and on weights and measures for 2 dynastic histories, which is why he is the conduit through which both Liu Hui's date and Zhu Changzhai's value for pi reach the present. At the Tang Imperial Academy, the classics program admitted 300 students a year, while the mathematics program admitted 30. A professor of mathematics held the lowest official rank there was, while his teaching assistant held no rank at all. Study ran 7 years, split between 2 separate tracks. On one, the 9 chapters, paired with Liu Hui's surveying manual, took 3 years, as much as any other text on it. On the other, the Zhui Shu alone took 4, and it is the only one of the 10 books that was subsequently lost. Examinations had 2 parts. One was a memory test, in which candidates were shown lines from 2 short auxiliary manuals with 3 characters covered and had to supply them. In the other, candidates were asked to write on the general meaning of a procedure, to elucidate the computation, to construct an algorithm, and, in the regulation's own words, to elucidate the structure and principle of the algorithm in detail. In the 7th century, the Tang state was examining its mathematics students on whether they could say why a procedure worked. The standard account of mathematical proof, hardened in the 19th century and still the one most people absorb, runs like this. Proof emerged in Greece, matured in Euclid and Archimedes, and is therefore a distinctively European inheritance. Other traditions computed, sometimes brilliantly, but they stated rules without demonstrating them. The French physicist Jean-Baptiste Biot put it in as many words in 1841, writing that Oriental nations limited their scientific writings to the statement of a series of rules, without requiring any logical demonstration. Karin Kemla, who with Guo Shuchun produced the 1,100-page critical edition of the 9 chapters and its commentaries in 2004, has spent a career taking that account apart, and her central move is to notice that it is circular. Suppose you decide in advance that the purpose of a proof is to place a result beyond any possible dispute. Then only one kind of argument can qualify, the kind that starts from stated assumptions everyone grants and proceeds by steps nobody can refuse, which is exactly the Greek geometrical method. The definition has quietly nominated its own winner. Kemla points out that working mathematicians today value proofs for a range of things other than certainty, for the clarity they bring and the understanding they produce, and she proposes that historians ask a different question. Not whether a tradition had proof in the Greek sense, but what different communities of practitioners were doing when they showed an interest in why a statement was true or an algorithm was correct. Applied to Liu Hui, the question becomes tractable, and the answer is that his commentary is full of demonstrations. They do not look like Euclid's. An algorithm, in Kemla's reading, can operate at two levels simultaneously. It prescribes a computation, and it argues. When Liu Hui shows that the elimination step in Fangcheng and the addition of fractions are both instances of homogenizing and equalizing, he is not merely noting a resemblance. He is establishing the correctness of one procedure by reducing it to another whose correctness is already understood. Kemla has also drawn attention to the Liu, a concept running through the whole text. She declines to translate the word and defines it as quantities that are defined only with respect to each other. Lai Chunfeng placed the Liu at the root of the entire structure. Because they are relational, operations on them are automatically general. Liu Hui states his circle result as a pair of ratios rather than a decimal for exactly this reason, and the answers to the well problem are given as ratios and immediately marked as such. Generality, Kemla argues, was the value the Chinese tradition prized, and it achieved generality without abstraction. Problems function the way a conjugated verb functions in a grammar book. Nobody thinks the point of the example is that particular verb. The single worked example of 3 grades of grain is not an instance of a general method waiting to be stated in symbols. It is the general method, expressed in the only register the tradition needed. Geoffrey Lloyd, who worked alongside Kemla on the essay collection about mathematical proof that she edited, holds a thesis that sits beside hers rather than against it. He accepts that the Chinese commentaries prove things. He also holds that an explicit theory of demonstration from stated first principles was developed in Greece and nowhere else. And he grounds that difference socially rather than intellectually, in the adversarial public argument of the Greek city against the court-scented discourse of the Chinese scholar official. Contributors to that same collection make a parallel case about the Greek side. The 19th century, critical editions of Euclid and Archimedes, the ones every modern reader depends on, reshaped diagrams in the direction of the ideal the editors already held. How much more Euclidean Greek mathematics looks, because of those editions, is an open question. The 9 chapters was printed in 1084 by the Song Department of the Imperial Library, and again, around 1213, by a scholar named Bao Huanji, who added postfaces to each of the 10 mathematical books. His printing is the earliest edition that still exists in any form, and what exists of it is chapters 1 through 5. Those sheets were traced by hand in 1684, passed through a series of private collections, and are now divided between the Palace Museum and the Shanghai Library. For chapters 6 through 9, everything depends on an encyclopedia. Commissioned in 1403 and finished 5 years later, the Yongle Dadian ran to more than 22,000 chapters, bound in 11,000 volumes. And it worked by cutting existing books apart and refiling their contents under classified headings. All of the 9 chapters went into it, dispersed. In 1772, the Qianlong Emperor ordered the collection that would become the complete library of the 4 treasuries. And the following year, when the editorial bureau opened, the philologist Dai Zhen went to work in it. He had made his reputation on the strength of his philology and his mathematics, and was so valued by the court that the emperor eventually awarded him a doctoral degree independent of examination results. Working through the surviving volumes of the Yongle Dadian, he gathered the scattered pieces of the 9 chapters back into 9 chapters, collated them, restored diagrams that had been lost, then produced the text that every subsequent edition has descended from. He also, by every indication, changed it. The clearest evidence is a remark by Liu Hui, a scholar of the following generation who went back over the work. Passages Dai Zhen had declared corrupt beyond sense, Liu Hui found he could generally repair. But where Dai Zhen had quietly altered a sound reading, Liu Hui could not correct him, because there was nothing left to compare against. The addition that carried Dai Zhen's text into general circulation compounds the difficulty. Kang Jihan, who owned the surviving song sheets, printed the 9 chapters in his own series, and the colophon on the last page announces that the Kang clan of Quafu recarved it from the traced song printed edition in the autumn of 1773. Bibliographers have concluded that both the claimed source and the claimed date are unreliable, and that the real basis of the printing was Dai Zhen's reconstruction from the encyclopedia. A text assembled out of a 15th-century filing system was presented to its readers as a faithful recutting of a 13th-century block print. Little of the encyclopedia survived the century that followed. Most of it was burned or carried off when Anglo-French forces took Beijing in 1860. Several hundred more volumes went in 1900, when the Hanlin Academy, the imperial college that housed them, burned during the fighting around the foreign legations. Something under 400 volumes survive today out of 11,000. The editors of the 4 treasuries had reconstituted hundreds of otherwise lost works from that encyclopedia in the 1770s, less than a century before the fires. What the text described had been forgotten earlier, and the forgetting went further. Counting rods had done more than arithmetic. Because the board was two-dimensional, its geometry could carry algebraic structure. By the 13th century, Chinese mathematicians had developed the method of the celestial element. A quantity multiplied by itself is its square, multiplied by itself again its cube, and so on upward. These are its powers. On the counting board, the powers were given positions, stacked above and below a baseline, so that an equation involving all of them became a physical column of numbers that could be shifted and combined as a single object. Zhu Shiji's Jade Mirror of the 4 Unknowns, from 1303, extends this to 4 unknown quantities at once, arranged around a central cell in 4 directions. Then the abacus arrived, in its familiar Chinese form in the 15th century, illustrated in a book of 1573 and codified in 1592 in Cheng Daoi's unified lineage of computational methods, the standard text for centuries afterwards. An abacus is faster than rods for arithmetic, and it is portable. What it cannot do is hold a 2-dimensional array. It is a device with 1 dimension and a fixed number of columns, excellent at addition and multiplication and useless as a medium for algebra. When the medium went, the methods went with it. The Mongols had ruled China as the Yuan dynasty, and one explanation offered for the neglect is that after the Ming drove them out, learning associated with the Yuan court fell under suspicion. What is not in doubt is that the texts, without living practitioners to explain them, became opaque. When Wu Jing compiled a comprehensive survey of earlier Chinese mathematics in the 15th century, he left out the celestial element method entirely, along with the technique for extracting roots that went with it. 2 prominent Ming mathematicians, Gu Yingxiang and Tang Shunzhai, appear to have been ignorant of the celestial element. On the standard account, Chinese mathematicians of the 17th century could no longer read Chinese mathematics of the 13th. It was in that state of amnesia that the Jesuits arrived. Matteo Ricci reached China in 1582 carrying his teacher's Latin Euclid, and in 1606 he began translating it with Zhu Guangqi, one of the most powerful officials of the late Ming and a convert to Christianity. Ricci translated aloud from the Latin, Zhu rendered the spoken Chinese into literary form, and in 1607 the first 6 books appeared as the elements of geometry. Their coinages are still the ordinary Chinese words for geometry, triangle, and volume. The translation stopped at 6 books because Zhu's father died, and he withdrew for the customary 3 years of mourning, and by the time he returned to the capital, Ricci was dead. Though the 10 mathematical classics are lost, Zhu Guangqi wrote, "This is not a pity, for they were nothing but worn-out shoes." Most of the 10 still existed on paper. What he meant was that they had dropped out of use. He was comparing a living Euclid against a body of work whose central technique nobody in China could still read. The reaction, when it came, took a peculiar shape. Rather than defend Chinese mathematics on its own terms, 17th-century scholars advanced the thesis that Western learning had originated in China in the first place, had been lost when the first emperor burned the books, and was now coming home. Mei Wending, the leading mathematical astronomer of the early years of the Qing dynasty, the last of the imperial dynasties, articulated the position fully and used it to organize a generation of work. His grandson Mei Zhucheng, working on the Imperial Mathematical Compendium of 1723, made the identification that gave the thesis its sharpest form. The algebra the Jesuits had brought, the method of the borrowed root and powers, was the same thing as the old Chinese celestial element method. Although the terminology is different, he wrote, in reality the two systems are the same. He was substantially right, and the identification did real damage, because it caused later commentators to read the recovered Chinese method through the Western one and to misunderstand it. It also did enormous good, because it made recovering the Song and Yuan texts a matter of national urgency rather than antiquarian curiosity. The bureau Dai Zhen pulled the jade mirror out of the same encyclopedia as the 9 chapters, and a wave of new research followed. In 1835, Liu Hui published a detailed working through of the jade mirror that made Zhu Shiji legible again, 530 years after the book was written. The modern argument about Chapter 8 begins from a received Western account that Chinese techniques for solving linear systems showed little development after the Han, and that determinants were discovered in the 17th century by Leibniz in Germany and by Seki Takakazu in Japan. Roger Hart's book of 2011, The Chinese Roots of Linear Algebra, set out to dismantle that account. Hart's central claim is about visualization. What made general solutions of linear systems possible in China, he argues, and what was absent from Greek and early European mathematics, was the two-dimensional display of a problem as a grid of numbers and the multiplication of whole columns of that grid by single entries from other columns. He does not deny that the procedure resembles what is now called Gaussian elimination. He says the resemblance is the least interesting thing about it, and that historians have used it to flatten a more varied set of practices into a single familiar shape. His most substantial technical finding concerns the ending of the procedure, the climb back up the columns, shown to be a sophisticated method for staying in whole numbers that later historians consistently misread by importing modern habits. The well problem, Hart argues, is not open-ended in the way modern readers assume. There is no evidence from the text or the early commentaries that anyone regarded it as having infinitely many solutions, and 721 is not a choice made to pin down a family of answers, but the output of a determinate calculation. Liu Hui's remark that the answers are ratios that can be scaled sits awkwardly beside that reading, and Hart takes it to describe how the numbers were obtained rather than how many solutions exist. He notes that the well problem teaches nothing, that there is nothing about it that is instructive either in the elimination or in the climb back up, and that its presence in the chapter therefore needs explaining. His explanation is that a separate family of determinant methods was already in use when the 9 chapters was compiled, that 5 of the 18 problems bear their fingerprints, and that the literati who wrote the chapter down understood the general procedure, but not the specialized techniques. Around that last point, Hart builds a claim about who actually did this mathematics. Chapter 8, he argues, records the working knowledge of anonymous practitioners, quite possibly illiterate, and what survives is what literati compilers were able to extract from them and willing to write down. The compilers were not disinterested. They sometimes credited mysterious recluses, apparently to make their compilations seem exclusive, and at other times denounced Fangcheng practitioners for using arcane techniques. Nothing the practitioners wrote, if they wrote anything, would have been collected or preserved. So the record is a partial transcript of an oral craft. Responses have been substantial and mostly technical. Joseph G. R. Carr, reviewing the book for the American Mathematical Society, made the point that matters most about the transmission story. Leibniz did not contribute to Gaussian elimination. Elimination appears in Europe on its own, without any determinants attached, in a French mathematician's book of 1560, and it runs forward from there through Newton and the 18th century textbooks to Gauss, whose name later mathematicians attached to it for reasons that have nothing to do with his having invented it. Determinants are a separate lineage, so even a demonstrated channel from China to Leibniz would not explain the elimination method at the heart of Hart's case. Jean-Claude Martzloff, whose own history of Chinese mathematics is the consensus statement Hart set out to overturn, reviewed the book warmly, called it unprecedented in precision and erudition, accepted Hart's reading of the ending, and then observed that neither Secchi nor Leibniz came to determinants by way of linear problems like the ones in Chapter 8. Both arrived from a quite different corner of algebra, by way of eliminating unknowns from equations that were not linear at all. Jens Høyrup, a Danish historian of ancient mathematics, has offered a third possibility that reverses the direction of borrowing. Comparing Chapter 8 against Greek sources and a collection of problems from Hellenistic Mesopotamia, written in Babylonia in the centuries after Alexander, he concludes that certain arithmetical riddles traveled into China without their methods, carried by a transnational community of traders, and that these imported problems prompted the Chinese creation of the Fangcheng method. On that reading, the problems are cosmopolitan, and the algorithm is Chinese. Kemla and Guo, in their edition, read the procedure as continuing past the triangular form to clear the entries above the diagonal as well, so that each answer is left sitting alone in its column, and they say the result is identical to a standard modern technique. Hart says flatly that they have used a modern technique to explain an ancient one. G. R. Carr, reading Hart, understood him to be arguing for something rather similar to what Kemla and Guo describe. The two positions turn on whether the operations are best understood as whole number moves on a physical board, or as the manipulation of numbers detached from any surface. Every version of the argument returns to the same question, and the missing board makes it impossible to settle. Chapter 8 records what the rods did. It cannot record what the board was, because the board was so ordinary to everyone involved that nobody described it. Everything downstream of that gap is reconstruction. Liu Hui annotated a text he believed had already been salvaged twice from a fire. Lai Chunfeng preserved inside that text the solution to the problem its commentator had abandoned. Dai Zhen assembled chapters 6 through 9 out of an encyclopedia that had dismembered them. Kong Jihan reprinted the result under a pedigree bibliographers do not accept. Luo Shilin worked out from written traces how to do something that had been ordinary craft knowledge 5 centuries earlier, and was by then as foreign as a dead language. Modern historians argue about whether the elimination stopped at a triangle and what the ending of the procedure looked like. Every one of the later figures in that chain was inferring the instrument from a record of gestures. Liu Hui's sentences about cutting are the earliest limiting argument put to work inside a Chinese mathematical text, and they describe a method that works by accepting an unavoidable remainder, and then arguing that the remainder does not matter. What is subtle is without form, he said, so why concern oneself with it? 2,000 years of the text's own history have consisted of the same operation performed on the text. Each recovery cuts a little finer, closes a little more of the gap, and leaves a residue that will never be recovered, because what it happened on was a flat surface that nobody thought to keep.